Okay, so today we'll, as I told you, today we'll start our discussion on tensor product of modules. So last time or in the last few lectures, apart from exact sequences and localization of rings modules, you also saw exact sequences and projective modules. So today we'll talk about tensor product, but let's just recall the universal property of tensor product. Yeah. So let R be a commutative ring with unity. So this will be the case throughout in this course. Yeah. All the rings we'll consider will be commutative ring with unity, and M and R module. Then we constructed S inverse M. Yeah. So we constructed the module S inverse M. So this was actually an S inverse R module, and hence also a S inverse R module. So put S inverse R module. S inverse M. So it's also an R module because any S inverse R module is an R module because of the natural map from R to S inverse R. Yeah. And it came with this map phi from M to S inverse M, which sends M to M over 1, and this map is R linear. Yeah. So R is an R module homomorphism. And the universal property says that given any S inverse R module N and any R linear map from M to N. So remember, N is also an R module because it's an S inverse R module, and M is an R module. So you can ask when a map from M to N is R linear. Yeah, so given any R linear map alpha from M to N, there exists a unique alpha tilde from S inverse M to N such that this diagram commutes, which means P followed by alpha tilde is same as alpha. Okay, that's what. Yeah, so this is the universal property of localization, which hopefully you saw in the notes. So one can prove this as a theorem, but one can also use the good thing about universal properties. You can use this to define the object as well. So you can define the localization of M to be an S inverse R module which has this universal property. Yeah. So you say that S inverse R module is localization of M if it has this universal property that given any S inverse R module and you have this you have a map from S inverse M to N. So meaning so this localization always comes with this map. So in some sense, localization is not just the module but this map as well from M to S inverse M. So the universal property will say something like that. Yeah. So given any so a module will be called localization if there exists a module together with a map M to that module is called the localization if it has this. But the reason we don't do it, define it that way is because the construction is very important of localization, and it's pretty straightforward, and one can one uses the construction very much. Yeah. So this is how these equivalence classes, etc., is how one thinks of localization, field of fraction, and so on. Yeah. So that is the reason. If you are talking about localization of rings, even there also you can use the universal property to define the localization. So one uses the construction quite prominently, and that is why people take this approach. But in tensor product, so we will use the we'll use this universal property strategy to define tensor product. So the point is, once you define using universal property, you still have to show that it exists. Yeah, and existence, of course, is then you construct how it works. So the construction which we did for localization, you do it and show that it has the universal property. So then you know that the localization exists, and you can show that it's unique as well because of this universal property. You can so there is a standard trick. So we will do this in tensor product, and in the same way you can show that. If you define localization with respect to universal property, you can show that this also is unique. Okay, so and the reason we define tensor product using the universal property is that in case of tensor product, the universal property is more important. So people use the universal property of tensor product more than, let's say, the construction. So once you see the construction, you will know why people don't use the actual construction of tensor product to work with tensor product. But the universal property is much more useful and helpful to do some computations or whatever, proof theorems and so on. Okay. So let's start with the definition of tensor product. So let M and N be R modules, and R mod. Is there any question? No. Okay. So let M and N be R module, and R module T together with an R bilinear map phi from M cross N to T. So what does it mean? So what does it mean to say phi is R bilinear? So it means that if you fix one coordinate M, fix an element M in M, then phi M dash is linear, which you can write it this way: phi M N1 plus R N2 is same as phi M N1 plus R times phi M N2 for all, and this should be true for all M in M. Yeah. So and linearity means this identity should be true for all N1 N2 in N and R in R. Okay, and similarly in the first variable. So phi should be linear in the first variable and in the second variable. So it's similar to bilinear maps from linear algebra, which you have seen. Yeah, just that instead of being over field, it's over a ring. Yeah, we are talking about modules, not vector spaces. So an R module 2T together with a R bilinear map is said to be the tensor product of M and N over R. If given any R bilinear map C from M cross N to A, where A is an R module, there exists unique R module homomorphism theta from T to A, such that theta composed phi is C. So that diagram commutes. So I should have drawn some picture here. So maybe I'll draw a small picture here. N to T is your this sometimes is called the structure map. And you have another bilinear map to A, which is denoted by C. Then there exists theta from, so this is unique, such and R linear such that this diagram commutes. So these are T and A are both R modules. So you want theta to be R linear map. So this is the definition of tensor product of M and N over a ring R. Yeah. And so, or maybe when a module is said to be tensor product of M and N over R. So what we'll show is that T exists and is unique up to unique isomorphism. Okay. Yeah. Okay. Okay. So something is missing. I don't know why it says. So maybe something got deleted. Okay. So the proposition says that T exists and is unique up to unique isomorphism, and it is denoted by M tensor N. So, I'll say exactly what it means to in the proof what this unique up to unique isomorphism means. So, in some sense, it's canonical. So, you know, many modules may be unique. Two modules may be isomorphic in many different ways. Yeah, or the same module may have some automorphism. So we are not talking about some isomorphism, but we are talking about some sort of canonical isomorphism. So it will make sense once I say what exactly the statement means. So I'll come to it in the proof. So in the proof, what we'll have to do is show that construct a module which will have this universal property. Yeah. And that will prove that T exists, and then we will show that any two. So in fact, maybe we can start with this uniqueness thing, yeah, and then the construction, because it's sort of independent. So uniqueness is just saying that if two modules have this universal property, then it is the two modules must be isomorphic in a unique way, okay, in a canonical way. So proof. So maybe let's just go through uniqueness first. So uniqueness is some sort of general nonsense kind of thing. So you does just this universal property, yeah. So same technique you can use for tensor in localization as well, if you use universal property to define. Okay, so let T be a tensor product, and T prime another guy is another tensor product. So let T prime from M cross N to T prime be another tensor product not sure, acting funny. Be another tensor product of M and N. Okay, so then that means it also satisfies this universal property. And then we want to show so now I'll say what it means unique up to unique isomer. That there exists a unique isomorphism from T to T prime such that let's give this some name, alpha maybe, such that some diagram commutes. So you have phi is a map from m cross n to t, and then if you compose it with alpha, then it becomes a map from m cross n to t prime. This should be same as phi prime. Okay. So this is what uniqueness means. So we'll show we will show that this happens. Okay. So this is what what is meant. Okay. So so this is what we have to show, that there exists an alpha such that alpha composed phi equals phi prime, and we want to show that alpha is unique. Yeah. So by universal property of T, and since phi prime is bilinear, we get we do know that there exists a unique alpha such that this which is linear, such that this diagram commutes. So alpha composed phi is phi prime. We don't know whether it's an isomorphism or not. Yeah. And then by using this universal property for T prime, remember T prime is another tensor product. So that also has a universal property. And using the bilinear map phi, we get a map alpha prime from T prime to T, such that, and again this is unique. So maybe there exists unique alpha prime, such that alpha prime composed phi prime is equal to phi. Yeah. So we get these two properties. Now, of course, we can. There is another map from T to T itself. Yeah. So there are two maps. One is alpha to alpha, alpha followed by alpha prime, and the other map is the identity map. Yeah. And what do they have in common? So if you consider alpha followed by alpha prime, yeah, and compose with phi, so so phi followed by alpha prime, this is same as and this by maybe let's call this 1 and this as 2. So this is same as alpha prime composed phi prime by 1, and this is alpha prime composed phi prime is same as phi by 2. Yeah. So so this map alpha prime composed alpha has the property so is a map such that this outer diagram commutes. Yeah. So phi followed by alpha composed alpha prime is same as phi. But of course, identity has the same property as well. Identity composed phi is also phi. Yeah. Identity of T, that is. So so by uniqueness of so remember there is a unique map, since T is the tensor product, there is a map from T to T. There exists a unique map from T to T, a linear map from T to T, such that this diagram commutes. So by uniqueness, we get that alpha prime composed alpha is identity of T. Yeah. And similarly, you can say that alpha composed alpha prime is going to be identity of T prime. So you just have to do it one more time here. Yeah. So that that proves that hence alpha and alpha prime are isomorphisms. Alpha is an isomorphism. And uniqueness is there in the construction and the definition of tensor product itself. Okay, so that proves the uniqueness of tensor product. The next thing we want to do is prove the existence. So uniqueness, it doesn't require anything other than the definition, more or less. You just apply the definition twice. So for existence, we will construct it. So as I said, the construction is a bit let's say unusable. I mean, it's not unreasonable, but you can't really work when you want to compute tensor product, you won't use this method to compute. But it will so whatever we do, we will be able to use this to prove that it has the universal property. Let's construct. So the point is, we want this T to be a bilinear T to be an R module, and we want a bilinear map to T, and eventually we want it to have certain universal property. Okay. So sorry, not proof is continuing, but this is existence. So let F M cross N be the free module, free R module over M cross N. Yeah, so you know what this means. M cross N is a set as well. Yeah, so a free module over a R module over a set, you know what it means. Yeah, so if you like, F M cross N is direct sum of R. Maybe take direct sum over all elements of M cross N. And just to sort of distinguish which copy of R you are taking, maybe we'll write R, yeah, R times M comma N. Okay, so this is how this is what free module over M cross free module over M cross N means. So there are many ways of thinking about it. You can also think of it as a set of all maps from M cross N to R such that it's supported on only finitely many elements, and away from finitely many it's 0. Yeah, so such set of such functions. And there is a usual component-wise addition and scalar multiplication. Okay, so this is your free module M cross N, and of course there is a natural map from M cross N to F. Yeah, so let's let so I don't want to call it phi because phi will be our I. So it's an inclusion map. So yeah, so Fm cross N. Maybe I'll just call it F instead of Fm cross N. Yeah, so that is easier to write. And the map is M comma N goes to maybe 1 times M comma N. Yeah, in this notation. So in terms of function, it sends it to a function which sends M comma N to 1 and rest of the elements to 0. Okay. So this is just a function because I mean there is no linearity or anything. Okay. So this is just some arbitrary function. And yeah, so now we want to cook up a bilinear are bilinear map out of this. Yeah. It, as such, the I is far from R bilinear, but we will quotient out F by certain relations so that what the end product we get is becomes bilinear. Yeah. So consider the map Q from F to F mod something. So we will have to quotient by something. So our submodule generated by these guys. Yeah. So what we want is, so right now you have a free module over all m comma n. But what you really want is this property should hold. Yeah. So it should become this, when we do this composition I followed by Q, then it should have this property that I mean m comma n1 plus r n2 should go to I of this composition will be phi, so it should go to phi m comma n1 plus r phi m comma n2. Yeah. So what you really want is that m comma n1 plus r n2, this minus m comma n1 minus r times so maybe 1, so there should be some element of the ring associated to, so or maybe 1 is redundant. Yeah. So whenever there is nothing, which means there is 1. Yeah. R times m comma n2. So this should you should have this relation there. Okay. And so, okay, let me write it a little more neatly. Comma, and so on, similar things. Yeah. So m1 plus rm2 R in R and n1, n2 in n. So these are some elements, and you consider the submodule generated by all of them. Yeah. So what you get is a submodule of F, and you quotient out by that. So our phi is going to be I followed by Q. Okay. So this is our phi, and this is a map from M cross N to this module. So we really want to give this module a name because this is going to be our tensor product. So call it T. Yeah. Yeah. So give me. So this is the tensor product of. So this we will show is has the universal property of the tensor product. Okay. So let's do this. So we'll have to show that phi is bilinear, and then we'll have to show that. So maybe I can say what we are trying to show. Yeah. So phi is bilinear. Want to show. Phi is bilinear, and t phi comma t and this map so maybe, and it has the universal property. So the point that it is bilinear is more or less by construction, and universal property is something which we will just check. Yeah, so it's not these are all sort of routine kind of thing, but one has to do it once. Yeah, not at all difficult. So so let's just check why it is bilinear. So that is just because we have thrown these relations, yeah. So we have said it should, we have quotiented out by these relations. So if you I think I forgot I forgot to start recording. Yeah. This. Oh, is it being recorded? Yeah, it is being recorded. Okay. Okay, so phi is bilinear. It has the the reason phi is bilinear is you just check, yeah. So phi of maybe one side we will check and the other one is similar, yeah. So n1 plus rn2 is as you know is same as q composed I of m comma n1 plus rn2, but what is q composed what is rather I of n1 cross so I is just the inclusion map, yeah, one times that, so you should just think of it as q of m comma n1 plus rn2, yeah. Okay, and what is that? So q of this is maybe you just look at the image of this guy. So it's just image. So maybe okay. I would have used the quotient notation, but maybe I'll just use bar. Yeah, m comma n1 plus rn2 bar. Yeah, but this is same as m comma n1 bar plus m comma plus r times m comma n2 bar. So yeah, bar essentially means q, applying q. Yeah, since m comma n1 plus rn2 minus m comma n1 minus r times m comma n2 whole bar is 0 in t. Yeah. So the difference of these two lies in the submodule you are quotienting out by. So that's why this relation holds. This is same as q of m comma n1, or rather phi of m comma n1. It's also q of m comma n1, but more precisely, this is same as phi of m comma n1 because you include it and then r times phi of m comma n2. Okay. Maybe I should have written this after this line. And this is equal to phi of m comma n1 plus r times phi of m comma n2. Okay, so makes sense that fees are bilinear. Similarly, linearity in first variable. So now what we want to do is check that this has the universal property. So let C from m comma n, m cross n to A be R bilinear map. Then what we have to do is produce a linear map from T to A such that the diagram commutes, and so that this is such a map is unique. Yeah. So what did we call it? I think alpha or something in this definition. Theta. Yeah. So we had theta from T to A. So let's just use the same. Want theta from want theta from T to A are linear such that first we apply phi and then theta, then it should be equal to C. Yeah. So how do you define theta of an element in T? So remember, T is this guy F mod. So it's difficult to give a map from T, yeah, because T is not a free module. But it's easy to give a map from a free module to something, and then check whether it factors through T or not. Yeah. So what we'll do is we'll define first a map from F to A. Yeah. So let theta tilde. So we want theta, but let's just define theta tilde first from F to A. So what we will do, F is a free module over m comma n. So what we do is we declare where m comma n goes for each m comma n in m cross n, and then it will determine what happens to every element of F. You just extend it linearly. Yeah. So we want m comma n to go to where should we send it to? So we want the diagram to commute, and it should with the C. So we send it to C m comma n. Yeah. And so more generally, if you have an arbitrary element of F looks like R m comma n times m comma n. So this indexing is by comma n in m cross n. So most of these. So you have to take finite sums. So so finitely many m comma n in m cross n will go to I don't know, summation r m comma n. So m comma n in m cross n, and maybe I should write finite here. So you only take finitely many of them, or you declare most of these r to be 0, whatever you like. Yeah, so this is the definition of theta tilde. So theta tilde is linear. Yeah, but it's a map from F, not from T. So now note that C is bilinear. So from there we will get that whatever this submodule is, I should have really given a name to this submodule. Yeah. So let me give a name now. This submodule, let's call it K. Yeah. So because it lies in the kernel of Q. So so maybe I'll write it here clearly. K is kernel of Q contained in F. Okay, so note that C is bilinear and hence so if you take any element of any of these generating elements, so K is the submodule generated by these guys. So if you take any of these elements of K with generators of K, then note C, hence C of these kind of elements. So maybe I'll just write it here. M comma n1 plus Rn2 minus M comma n1 minus R times M comma n2. So C is bilinear, R bilinear. So remember C of sorry, not C, but theta is what I mean. So theta tilde of this guy is just C by definition is just C of M comma, so theta tilde we are extending it linearly, yeah, so the M comma n1 plus R n2 minus C of M comma n1 and minus R times C of M comma n2. Yeah, so that is the definition of theta tilde. This bracket is redundant. Yeah, and C is R bilinear means this one splits and you get the right hand side. So this is 0. So this is where C is, since C is R bilinear, is bilinear, R bilinear. Yeah. So this implies K is contained in kernel of theta tilde. Yeah. So you get a map. So there exists a map. So theta tilde by first isomorphism theorem. So there exists theta from T to T to A. So the kernel of theta tilde contains K. Yeah. So there exists a map from T to A such that which we call theta, such that this has the property that this diagram will commute. So so you first go Q and then go theta, and that is same as theta. Yeah. So maybe I'll draw a picture again. T to A is your theta. You already we already had a map from F to A, which was theta tilde, and we have this map Q. And since which had the kernel K, and since the kernel is contained in kernel of theta tilde, we have this this diagram commutes. So this is first isomorphism theorem. So in fact, if you know that the kernel is exactly K, then you can say that these two, this theta is actually an isomorphism, but that we don't know. Yeah, we only know that the kernel is contained in A. Might be the zero module, then everything is contained in the kernel. Yeah. So we get this, and We obtained our map theta. We have to show it has all the nice properties, so it is unique. So actually uniqueness, so it has this, I mean, first of all, it has the property that theta compose phi is C, and then it is unique with this property. Yeah, so let's compute theta compose phi. Yeah, so we want to show this theta compose phi is C. So theta compose phi is let's just compute it. So theta compose. So remember, phi was q composed I. Yeah. So we'll just do formal calculation. So q composed I is phi. Now theta compose q is theta tilde. So this is theta tilde composed I, and what is theta tilde composed I? So you just think about it. I is the map from m cross n to f. And if you do theta tilde, then basically you are getting just C of Mn. Yeah. So you are including m comma n to m cross n to m. So remember, this is map m cross n to f, which is just the inclusion map, followed by theta tilde, which sends m comma n to C m comma n. Yeah. In A. Yeah. So this is just C, the bilinear map C. Okay. So so that proves that it has this universal property, and the uniqueness is also sort of straightforward. So everywhere, I mean, you can appeal to first isomorphism theorem itself. This theta itself is unique in some sense, and there exists unique theta which makes this diagram. Okay, or you can check directly that that this is unique. So we are close to end of time, so I'll stop here. But sorry for going over and all the interruptions. So so do you have any questions? Sorry, this Zoom vanishes, so I'm not really sure if you heard all the lectures.
Yeah, we heard most of it. It's not.
Okay. Okay, good.
So I had one question, which is, so as we have seen that localization commutes with tensor, right? So I mean, if you
so we will see that maybe later on. We haven't seen that.
Okay, we haven't seen that, but I mean, so that's a fact. That's true, right? I mean, if you have a prime ideal P in A, then if you localize M tensor N at P, then that's the same thing as M localized at P tensor N localized at P, right?
Yeah. So in fact, we will see that localization, you can realize it as a tensor product as well, and we will see commuting of tensor products.
Yeah. So I was wondering that perhaps there's some geometric way to see it. So for example, if you look at modules over Z, then and let's see, then if you localize, so
it will become clear. So okay, so I'll give you some idea later on. But before that, are there some questions on the construction so far? So this is more or less the end. You have to show that theta is unique, but that's about it. Yeah. So if there are no questions, then maybe I'll answer Balarka's questions. Yeah. Okay. So what you're asking is whether so the point is S inverse M you do, yeah, where S is some local ring. This is same as this we will see is same as S inverse R tensor over R M. Okay. So so once you prove this, then and then some more basic properties of localization as well we will see. So now you are asking if S inverse M tensor with A is same as I don't know. Commutes with localization means what? Yeah.
Yeah, I just mean that I mean M M tensor n localized at S is the same thing as S inverse M tensor S inverse n.
So you are asking whether, so it must follow from something like this.
Yeah, it should follow from this.
Yeah, whether it is S inverse of M tensor. Yeah, so this and some other basic properties which we will see. Yeah, so okay, so it follows from one of these basic properties. Yeah, so so this is S inverse R tensor over R M tensor R n. Yeah, and this is S inverse R tensor over Rm. So yeah, so you will you can yeah. So I'll have to list down a bunch of other properties which we will do next class anyway. Yeah. So then we can discuss this.
Yeah, for sure. Okay.
Yeah.
Thanks. Yeah.
Okay. So next class we'll see some basic properties of tensor product, and I'll answer more questions on this next class. Yeah, so I don't know, you may have, do you have a class right now? Okay, anyway, I think I shouldn't go over too much. So I'll see you guys tomorrow.
Yeah, thanks.